spectrum. So by now you have got a fair idea what happens when a photon is absorbed and when a photon is emitted. So here these diagrams will clarify the thought further. So in the first case you see absorption spectrum, where an electron jumps from a lower energy level to higher energy level, and as a result it absorbs a photon. So in this case the spectrum that is obtained, that means the lines which you see where which shows electrons jumping from lower energy level to higher energy level, that forms the absorption spectrum. Whereas in the second case where you see that the photons are getting emitted at every process, so these lines together form the emission spectrum. So this is how the absorption and emission spectrum look like. So how do we mathematically describe an absorption spectrum and an emission spectrum? So for example, in the absorption spectrum, here the energy at the ground level is E1, and let's say that the energy at the excited state is E3. So we can say that when some additional energy is given to this ground state, now that additional energy is the energy of the photon, then this electron jumps to the excited state, which is E3. So you can say E3 minus E1 is equal to h nu. So more is the difference in the energies of the two levels, more is the frequency of the radiation. So that means if you want to make this electron jump from E1 to E4, so the difference between E1 and E4 is more, therefore you need the photon's frequency to be more. So the frequency of the photon would also be more. So more is the difference, more is the frequency of the photon, and less is the wavelength, because frequency and wavelength are inversely related to each other. So more is the difference between the energy levels, more is the frequency of the photon, and less is the wavelength of the photon. Now if you talk about the emission spectrum, in this case you can say, let's talk about this transition from E4 to E1. So here you see that energy at 4, that means E4, when it releases a photon, let's say that it released a photon of energy h nu, then this comes back to the ground state, which is E1. So from this also you can say E4 minus E1 is equal to h nu. Right? So in this case, like here you see three transitions, right? One is from 4 to 1. So this transition is from energy level 4 to 1. This is from 4 to 2, and this one is from 3 to 1. So these are the three transitions which are taking place. Now out of these, the difference in the energies is maximum in 4 to 1 transition. Therefore, the frequency of the photon emitted will be maximum in this case, and the wavelength of the photon emitted will be minimum in this case. So in this fashion, looking at the difference of between the energy levels, you can predict the frequency and wavelength of the photon emitted. Now let us specifically talk about the hydrogen spectrum. So when we look at the hydrogen spectrum, we see that it consists of discrete lines, and that is where the concept of the line spectra comes into picture, which Rutherford's model failed to explain and was further and then later explained by the Bohr's model. Now in hydrogen spectrum, we again have two types of spectrum. One is the emission spectrum, where we see discrete bright lines in dark background, and the other one is the absorption spectrum, where we see dark lines in bright background. So basically in both the cases you see discrete lines, right? Now here on the screen you see various names like Lyman, Balmer, Brackett, Paschen, and Pfund. So what are these? So these are basically series which are part of the hydrogen spectra. So in the hydrogen spectra you have series of such lines, and each of these series are located in different wavelength range. For example, the Lyman series is located in the ultraviolet region. The Balmer series is located in the visible region. Brackett, Paschen, and Pfund, they are located in the infrared region. So how are they located in these different regions? Because they have different range of wavelengths. And there were different scientists who actually discovered these series, and that is why these series are named after their discoverers. So we have something called the Balmer's empirical formula, which helps us to calculate the wavelength of various series of hydrogen spectra. Now this formula, which is called Balmer's empirical formula because it was deduced by Balmer, goes somewhat like this. 1 by lambda is equal to r 1 by 1 square minus 1 by n square. So this is the empirical formula for Lyman series. What happens in Lyman series? The lines fall from higher energy level to n is equal to 1. So in this case, the value of this n could be anything after 1. N could be 2, 3, 4, 5, 6 or anything. So from any higher energy level, when it falls back to n is equal to 1, these lines, they together form the Lyman series, and the wavelength for the Lyman series can be calculated using this formula. Similarly, the next series is the Balmer series, where the value of n1 is 2. That means all the lines fall to n is equal to 2. Therefore, the value of n in this case would be 3, 4, 5, 6 onwards. So it would be anything beyond 2. Next is Paschen, where this is 3. That means everything falls to 3. So this is basically Paschen. And this one is bracket, and this is P fund. So in this fashion, here the value of n could be 4, 5, 6 onwards, anything. Similarly, bracket and P fund. Right? So in this fashion, using these empirical formula, you can easily calculate the value of wavelength. Now, if you actually calculate the value of these lambda, you would see that the lambda for Balmer series, it lies in the visible range. Similarly, the lambda for Lyman series, it lies in the ultraviolet range, and so on. So that's about the hydrogen spectrum. Now let us quickly talk about X-rays. Now what are X-rays? I mean, where do you use this term X-ray? Many times when you get a fracture in some part of your body, or sometimes you are having severe backache and the doctors advise you to get an X-ray done. And what is that X-ray? When you get an X-ray done, it gives a picture of the internal structure of that body part. Right? So what is so special in X-ray that the rays are able to penetrate inside your body and get an image of it? So how does that happen? So that happens because of the properties of X-rays. So X-rays are very short wavelength electromagnetic waves. They are invisible. You cannot see them. So if you have ever been for an X-ray, you would see that you can see those rays. However, they travel with the speed of light, and just like light, they also travel in a straight line. They do not carry any charge. They affect photographic plates, and this is one reason why we are able to take X-rays of different body parts, because on the photographic plates you see that impression, right? So that is possible because the X-rays are able to affect the photographic plates. Now when you look at the X-ray spectrum, it again consists of sharp lines. In fact, we talk about the KLM series of X-rays. So what are these different series of X-rays? Now if we talk about the K series of X-rays, it means that now, how are X-rays produced? Normally, when electrons moving at high speed, they strike a target. So when they strike a target, the electrons are emitted from the target, and as a result, X-rays are also emitted as a result of this process. Now, for K series, if an electron strikes the target, K shell, that means K shell of the target is hit. In that case, vacancy is created in the K shell because an electron is released from the K shell. So immediately an electron from some outer shell, maybe L, M or N, jumps to fill that vacancy in the K shell, and as a result X-ray is emitted. Because we know that whenever an electron from any outer energy level, whether it is L, M or N, whenever an electron jumps to K shell, what happens? The electrons are actually jumping from higher energy level to lower energy level, and as a result X-rays are emitted. So this is how X-rays are emitted. Now similarly, when you talk about the L series of X-ray, L series means the electron strikes the target's L shell. So that means an electron goes out from the L shell, right? As a result, vacancy is created in the L shell. To fill this vacancy, electrons might come from M or N shell and fill that vacancy. Now, the moment these electrons come from higher energy level to the L shell, the X-rays are emitted. So these are called the L series of X-rays. So similarly, you have M series, N series, and so on. And how do we name these lines? So the transition which happens from L to K, that is called K alpha. The next line is K beta, the next line is K gamma, and so on. Similarly, the first line of L series would be L alpha, second line would be L beta, and so on. So this is how we name the lines on the X-ray KLM series. And the characteristic wavelength depends on the nature of the target material. So looking at this energy level diagram, you can say that the energy at the K level is greater than L, is greater than M, and so on. And how do you calculate the characteristic wavelength? So the formula is again similar to the empirical formula of the hydrogen spectrum. It is 1 by lambda is equal to R Z minus B whole square 1 by N1 square minus 1 by N2 square if the transition is taking place from N2 to N1. So here B is a constant, and that is why